Good afternoon, everyone. Thanks for coming to this seminar. My name is Miles. You can also call me Xia or Zhou, anyone. My topic today is exact and heuristic solutions for demand management problems in public transport. Let's start with an example. We want to plan a trip from a Carnegie station to the University of Melbourne. The Google Map can always provide different suggestions for you. If you want to travel during the off-peak hours, it takes around 35 minutes. But if you want to travel during the peak hours, for example, at 8:30, it takes around 42 minutes. The actual 7 minutes are caused by congestion delays. Similar things happens when we decided to travel during peak hours, but we choose different route. For example, we choose one route with more transfers. As shown here, it takes around 56 minutes. We can find when we make decisions to plan our trip on time and the route, we will get a different result. We call these combinations of time and the route is the travel option here. Normally, passengers are expected to choose the most popular route and times that they can find. If too many passengers choose the best of travel options, that will cause a problem, traffic congestion. Because of such temporal and spatial imbalance between the demand and the service supply can cause severe traffic congestion. Normally, there are two ways for traffic congestion relief. The first one, we increase the supply capacity. For example, we can invest more trains to the system, or we can also increase the frequency of train so that we can further balance the demand and the supply for congestion relief. The second method, we keep the service supply fixed, but we increase or we redistribute the demand over time and route. For example, we keep shifting passengers out from peak hour to off-peak hour, from popular route to alternative route, so that we can further rebalance the demand and the supply. This is the main idea of the demand management. Let's see examples of the demand management work. We will see some basic skills. The first thing that, as we can see here, we have one origin and one destination. These passengers are expected to travel from origin to destinations. For these passengers, they have two options, option 1 and option 2. Option 1, waiting for train 1, option 2, waiting for train 2. Each train have the capacity of 100 users. Now we have 200 users in all. This C1 is the expected travel cost of choosing option 1. The F1 is the number of passengers choosing option 1. When F1 is within capacity, then the C1 will equal to 80. But if F1 is over capacity, then 100 of them can board the train. The remaining passengers will be left behind by the train 1, and actually they will take the train 2. For these passengers, they will incur actual congestion cost, 200. For F2, if F2 is within capacity, the C2 will equal to 120. But if F2 is over capacity, then the C2 will equal to infinity, because we don't have a later train than the train 2 that can pick up the passengers left behind by train 2. So we set the infinity cost penalty for C2 if F2 is over capacity. Initially, all passengers will choose the best option. So that means all passengers will choose the option 1. And you can find if too many passengers choose option 1, congestion happens. If, as you can see, all passengers choose F1, the C1 will equal to 140. That means 100 of passengers will be left behind by train 1. And some passengers will change their mind because they can find a better option now, option 2, with the cost of 120. So some passengers will change their decisions from option 1 to option 2. C1 and F1 will decrease until one point that C1 and C2 will equal to the same travel cost, 120. Then we can find for all passengers, they don't have any motivation to change their behavior because they cannot further reduce their travel cost by changing their decisions. And we can find for this state, the F2 equal to 50 and F1 equal to 150. This state, we call this as the user equilibrium state or the user optimal state. In the user equilibrium state, all passengers will keep their original decisions because they won't have any motivation to change their decision. Actually, these user equilibrium solutions is also used to represent the actual passenger distribution in real life because it's a very stable state. But you can see here, even in the user equilibrium state or the user optimal state, there's still some congestion happens. You can find for these 50 users, they were left behind by the chain one. So if we want to further decrease the travel cost, what we can do? Actually, we just keep shifting passengers out from option 1 to option 2. We can find the total cost of the user equilibrium state is 24,000. If we keep shifting passengers out until one point that for both the options, they all have 100 users, then we will find all passengers can board the train they are waiting for. That means no congestion happens here. And we can also find the system cost now is the minimum one, with just 20,000. We call this system state as the system optimal state. The system optimal state is an ideal state, won't happen automatically in the real life because you can find there's still some cheap trips for passengers choosing option 2. But the system optimal solutions is useful to represent the ideal lower bound of the system. Actually, the system optimal solutions is preferred by the government or by the service provider because no congestion happens, no one will complain. The question here is, if we want to get the system optimal solutions, what we can do? We want to persuade some passengers change their behavior from UE to SO. For these 50 passengers, we need to shift them from option 1 to option 2. Then we can get the minimum congestion cost system state. If we do nothing, that won't happen. But if we provide incentive to these 50 passengers, of course, they will change their behavior because they can get the compensation incentives. This is the idea why the incentive design can relieve traffic congestion because they attract more passengers from the congested area to the free area so that they can further reduce the traffic congestion. And we can find if we want to design some incentives, of course, we need to know more of the user equilibrium modeling and the system optimal modeling. Let's see how we model the user equilibrium problem and the system optimal modeling. As we discussed in the previous slide, in the user equilibrium models, the users keep change their decisions until the system is stable. All options will share the same option cost. So we define the objective functions to minimize the difference among different options. This upper letter K is the set of OD pair. This upper letter T is the set of departure times, available departure times. This upper letter R is the set of available routes. This upper letter Q is the set of passenger distributions over K, T, and R. This AVC here is the option cost of choosing T and R. This AVC K star is the option cost of the best option. This QKTR is the passenger demand choosing T and R. Then we can find here, if the demand is 0 for that option T and R, we will use the default of free flow cost to represent the option cost. But if we have demand here, we will use the average cost to represent the option cost of choosing T and R. For the system optimal system, we assume system keep trying shifting users until the system optimal state is achieved. The objective functions is that we want to minimize the total system cost. This upper letter IKTR is the passenger group choosing T and R. And we can find for both user equilibrium modeling and system optimal modelings, one key variable here is that CKITR. We need at least CKITR to model both the user equilibrium modelings and the system optimal modelings. So the point here is that if we get the information of the demand decisions, how can we find the CKITR? We need to further understand how we evaluate the travel cost. The travel cost is defined as the weighted combination of waiting time, in-vehicle time, early arrival time, and late arrival time. For example, if the passengers choosing the departure time of 7:30 a.m. and the route is R1, the in-vehicle time for route R1 is 60 minutes. The target arrival time for this passenger is 9 a.m. If we know the information of the arrival time, 8:50 a.m., then we can find the waiting time is 20 minutes. The in-vehicle time is 60 minutes. The early arrival time is 10 minutes. The late arrival time is 0 minutes. Based on this data, we can calculate the travel cost for this passenger. So we can find, as we define the problem as the demand management problems, as we discussed before, all the schedules and the service will be fixed. So that the key point for the travel cost evaluation is the arrival time. If we know the arrival time for these passengers and we know the passenger's decision of departure time, then we can directly calculate the travel cost for this passenger. This is just a summary of how this problem works. We have such passenger's decisions. This K is the OD pair. This T is the departure time. This route R is the route. And then we have such a matrix of passenger decisions. For each options, we will have lots of passengers here. If we have these demand decisions, how can we calculate the travel cost? Then if we get the travel cost, we will evaluate the average cost for modeling the user equilibrium problem. And we summed all these travel cost users. Then we can modeling the system optimal problem. The key point here is we need to find a way to find the relationship between the demand and the travel cost. Let's start with a simple network, just one single line, and one origins, and we have several destinations, and the passengers can also board here, board here. For these downstream passengers, we can find their travel arrival time are influenced by the upstream passengers, because you can see if the train is full when the train passing through the downstream stations, no matter which kind of decision these passengers make, they all cannot board the train. But if we still have some capacities, then these passengers can board the train. So the travel cost, the average cost of these passengers will be decided by the upstream decisions. That means we have interactions between OD pairs. As you can see, we define some specific formations to calculate the cost, in previous examples. But actually, we don't have these example formulations because for this F1, even we know the values of F1, but they are influenced by the upstream stations, so that we cannot only based on F1 to calculate the travel cost. That means this cannot work anymore. Such interreacting OD flows is more obvious in the multi-line network. As you can see here, in the multi-line network, we have several lines that they will interact with each other. And for these passengers, for example, the passengers from 4 to 14, they will transfer at home and at Merity. And you can find if they come to the second transfer station at Merity, they will compete with the other OD flows from 1 to 14, 1 to 14, 2 to 14, 3 to 14. These passengers need to compete with all the other OD flows. Then the problem arises. Who can board the train? Who should have the priority to board the train first? And you can find if you decide let different passages come to the chain first, it will cause different system state in the end. Let's further explain this in detail. You can find we have two transfer stations here. For the passages, when they come, then when first come to the first stations, they will compete with one OD flows here. And when they come to these transfer stations, they will need to compete with the other incoming OD flows too. The question here is, if the passengers make decisions to choose the T11 for their first trip, then when they come to the transfer stations, we don't actually know which for these passengers they can take for T2A and T3B. That means we cannot evaluate the travel cost for these passengers. And the second thing could be when we're modeling the user equilibrium problem. As we mentioned before, the objective function is minimize the option cost difference. And we can find the definitions of the option cost here. It's a very complicated part to evaluate because we don't have formulations to evaluate the CIKR and the Q relationship between this CIKTR and the QKTR. So it's a bit hard for us to model these user equilibrium problems using exact method. Then we'll consider whether we can use the heuristic method to model this user equilibrium problem. Of course, we can. If we can use the summation to decide who will which chain for T2A and which chain for T3B, then we can find the relationship between the demand and the travel cost. The summation here will decide which passengers can board the chain, which passengers will be denied boardings. And we will further explain simulation in the next slide. For the user equilibrium modeling, we want to minimize the gaps. So the descent directions for our heuristic solution algorithms is that we always shift passengers from expensive options to cheap options. When we shift out passengers from the expensive options, that will relieve the congestion layer. The option cost of the expensive will decrease. And the similar things happen to the cheap options, they will increase. Then we can minimize the gap. The step size is decided by the golden search method that we find a specific step size for each OD pair, each options T and R, so that we can, if the gap is huge for a specific T and R, we will increase the step size. Then we can find the user equilibrium solutions to minimize total system difference. This is the introduction of the simulation. The key point of the simulation is the network loading engine. We put lots of input, for example, the schedules, informations, the train capacity, and the passenger decisions. Then this network loading engine will output the result at arrival time for all passengers. This is the queuing part of the simulation, that all passengers will wait at the transfer stations, and then these queuing sections will decide who will come first, who will come next. This is adopted by this paper. That's all the modeling part for the user equilibrium problem. But for the system optimal modelings, as we can see, the objective functions is the sum of all passengers' travel cost. If we can find a simple way to represent the relationship between the demand and the travel cost, maybe we can solve these system optimal solutions using the exact way instead of the heuristic method. Okay, the same problem here is we need find a way to decide the T2A and the T3B. We have two methods. The first method, we consider, we assume we always have enough chains, and there is no denied boardings in the system optimal state. This is inspired by my previous examples. We keep shifting passengers from option 1 to option 2 until no congestion happens. No one will be left behind. Then we can find for the T2A and the T3B, we can always find a specific T chains for T2A and T chain 3B. Then we can as we'll know the chains that for each connection, we can find the level time. Then we can evaluate the travel cost for this passenger. This problem will be we can pre-calculate all the travel costs for each decisions. As long as you tell me the decisions, we will pre-calculate the cost. You needn't worry about it. You need to compete with the others. This computation will be decided by the optimizer. The second method is that we assume all passengers will not wait for more than 2 chains. That means we will provide a set of chains for T2A and a set of chains for T3B. So if you already make decisions choosing T11 at first, then you will get 9 possible travel costs. We can pre-calculate at least 9 travel costs for you. And the problem is similar with the previous one. It's linearized. The passengers only need to decide which options, and the optimizer will decide actually based on the capacity constraint, which possibility you need to take. And we model this problem in MiniThink, and we can solve it deductive from the Globee. It's quite quick. This is our case study here. We consider the Hong Kong network. You can find for this network, we set 4 origins, 1, 2, 3, 4, and we set 3 destinations, 13, 14, and 15. This is the only demand that we considered. This 13 and this Koala Bay, the demand is 5,356. The question here is, how can we assign these problems to the system so that we can get the user equals to distributions and system optimal distributions? This is the baseline that we considered for the user equivalent modelings. We consider the first baseline is the MSA method. The MSA method is always used to model the user equivalent problems in public transport. And the key point of the MSA is this flow updating formulations. This VAN is the flows. A is the option, N is the iteration. This alpha is the step size. This FA is a side demand. And you can find here, for the first iterations, F will equal to 1,000 for the best option. And the flows, for the other flows, the first iteration will be 0. When you come to the next iterations, the F1 will also, FF will also choose the best options. After the first iterations, the best option is option 2. So that FA will equal to 1,000 and all the others will be 0. And I use this formulation to update the flows of each options until the end. The main difference of the MSA method and our method is that the first thing is that the half actually use the fixed half 1 second, 1/3. But we choose the gap-based descent step size. The second difference is the descent directions, that they always shift passengers to the best options, but actually we shift from worse options to good options. So it will be a set of options that we can accept the passengers. The second baseline is the day-to-day learning method. The main idea of the day-to-day learning method is the predict cost. That, for example, if you want to predict the cost of your current decision, you need the actual cost of yesterday's data. You need the predict cost of yesterday's data. Based on these 2 data, you can get the predicted data of today. And based on this predicted cost, you can find the probability of these passengers choosing each option. Based on the possibility of each options, then we can update the flows of that options. So the main idea of the day-to-day learning is to simulate the user's stochastic choice based on probability, and this probability is decided by their predicted cost. This is the result of the user equilibrium modeling. This ADA-GDD is our method, adaptive gap-based descent direction algorithms. We use the system relative gap to measure the solution performance. The relative gap represents the difference between our current system and the ideal system. The ideal user systems is for all options. All options with demand will share the same travel cost, so we measure the difference. And we can find all methods can find the solutions with the relative gap of only 0.19, but that values for the MSA method and data learning method is 0.8 and 1.2. It's quite bigger compared with our method. The baseline for the system optimal modelings, we use the approximate system optimal modelings. The main idea of the system optimal, the approximate system modelings is that we use the estimation and the heuristic algorithms to minimize total system cost. It's quite similar with the user equilibrium modelings that we use the similar simulations, we use the similar heuristic algorithms, but the difference is we replace the objective function from minimize the option difference to the total system cost. And the second difference is that the descent directions for these approximate system solutions, the descent directions is keep shifting out passages from the congestion area or congestion options to alternative options until the congestion cost is minimized. And we can find the solutions of the system optimal modelings. This is the user equilibrium models of the system cost. And this is the both of the latter two is the system optimal result. For the approximate system optimal solutions, we can find from the UE to the SO, the potential is only 17%. But if we consider using the exact system optimal solutions, then the potential is 36%, near double of the potential. The potential is used to evaluate the current systems because for the incentive designer, the first thing that they need to do is to see if I propose some incentives, how much I can benefit. Of course, we need to know the lower bound of the potentials so that we will evaluate whether we need to implement some incentive to the system or not. If the potential is 0, that means you need, no matter how you design incentives, this user equilibrium solutions won't be improved for congestion relief. Let's say some practical implementations of our models. The first one for the user equilibrium models. We can find actually the user equilibrium models can be used to evaluate the network designs. As we mentioned before, the user equilibrium solutions is also used to represent heuristic passenger distribution in an existing network. So whenever we get a new network, we will evaluate the potential passenger distribution to see whether we have too much traffic congestion or not. These are the examples of the Hong Kong network. Before 2020, this is the Hong Kong network looks like. But after 2020, they extend some lines. For example, they connect the stations from Taiwan to Diamond Hill, and the Diamond Hill to Hong Martin, and from Hong Martin to Hong Kong. And they further extend the line of the Green Line from the Hong Kong to Admiralty. Then they do such extensions. They want to know if I do such adjustment or extensions, how much benefit we can get. We can use our user equilibrium models to find the potential. The left side is the previous network's congestion levels. The congestion level is defined as the demand over capacity. Means if the congestion level is 1, that means the demand equal to capacity. But if 2, that means the demand is twice the capacity. This S1, S2, S3, and 4 are 4 stations that we choose. These hatch patterns for each unit you can find. For the horizontal hatch patterns, horizontal is around the corresponding congestion level is between 2 to 2.5, and this slope lines is here between 1.0 to 1.5. Then we can for this current network with extensions, congestion has been relieved with the hedged congestion part disappear, and it will come to a more uniform passenger distributions. That means the total system congestions has been relieved. And we can make a conclusion here. The new design is good enough to relieve traffic congestion. In practical implementation of the system optimal models, what the system optimal can do in practice. As we mentioned before, the system optimal represent the lower bound of existing systems. That means if we want to further reduce traffic congestion in existing user equilibrium solutions, we need know more information of the lower bound so that we can know whether we need to implement incentive or not. The system optimal modeling can help us to target the most potential passengers. As we mentioned before, the service provider or government need to invest some money for congestion relief. But if we don't have enough money, we have limited money, we should think about how we invest these monies to reduce the most congestions. The first curve is the OD cost of the UE and SO. The second, this OD pair 113, 114, and 115 you can find here. This 13, 14, and 15, 2, 13, 14, and 15 you can find here. These impacted users are found by comparing the UE and SO, because for both the UE and SO, we all have passenger decisions. And for each OD pair, each options, we will compare these two solutions to see whether they are same. Then we can find some impacted passengers that they need change their behavior so that we can find solutions closer to the system optimal solutions. We can find different impacted users. And this is the cost reductions, the average cost reduction that we can find. If we can see, we use the cost difference, the OD cost difference, and the impacted users, then we can calculate the expected average cost for each passenger shifting. That means, for example, for the passenger 313, if we can shift 1 passenger, then we can get the benefit of $22. That means you try your best to invest these passengers, then we can get the best benefit. By comparing the user equilibrium solutions and the system optimal solutions, you can always find the most potential users so that you can assign this limited many resource to these passengers for the maximum congestion relief. The last practical implementations of our models is the incentive designs. As we mentioned before, user equilibrium solutions and system optimal solutions can be used to guide the incentive designs. But how? As we mentioned before, both the user equilibrium modeling and the system models, they use the relationship between the Q and C, the travel cost. What we can do is to design incentives to control the demand. That means if we can control the demands from the user equilibrium demand distribution to the system optimal distributions, then we can further reduce the traffic congestion. So we design some incentives. That means for each KTR, the K OD pair T and R, we we implement some incentive here. Based on these incentives here, you will find the user equivalent solutions will be changed because you implement some incentives, and some passengers can find a cheaper option now, so they will change their behavior. Based on this method, we will control the QKTR. Then we can further control the total system congestion. So the task for the incentive design is we need a method to control the incentive for each available option. This is the traditional ways of how the incentive is designed. For the traditional ways, they will have some incentive proposals, and then based on these proposals, they will propose some incentives, and they will evaluate the incentive using the user equivalent model. Then we'll come back. For the incentive proposal, the most common things that we used in practice is to implement incentive in off-peak hours. So that most papers that discussing off-peak hour shifting is that they implement some incentive to off-peak hours and adjust the amount of off-peak hours to see whether they can further reduce the traffic congestion. For the reverse engineering framework, it's a bit different. We don't have, we replace the incentive proposals with the flow gap informations. That means we will keep compare the existing systems with the system-optimal systems to see the difference of each option's passengers. Then based on this difference, we will propose some incentives. Then we will evaluate the incentive and come back to evaluate the new existing systems with the system-optimal state. The main idea here is, for example, if we choose option 1, for the option 1, in the user equivalent solutions, it told us that only 100 users here. But the system-optimal solution tells us that for the option 1, we need 500 users. So for the incentive designs, we will increase the incentive in option 1. Similar things happens to all options. We will further update the incentive for several iterations until the gaps between the user equivalent flows and the system-optimal flows are closed. Let's see the result. We have two baselines here. The first baseline is the traditional framework using off-peak hour rule. The second baseline is the gap-based, gradient-based framework using user equivalent solutions. For the TOP method, it's the method that we mentioned before. It's keep implement incentive to the off-peak hour times to attract more passengers for congestion relief. The gradient-based framework using user equivalent solutions is an idea that the system will keep trying to find the congestion state, congestion area, and they will put an incentive to the alternative area to attract passengers from the congested area to the alternative area. Our method is called reverse engineering framework using the exact system solutions, i.e. ESO. This is the idea that we keep comparing the existing systems with the ideal optimal systems. Then we will update the incentives. The main difference of our method and these two baselines, that's for these two baselines, actually they don't need to worry about the system-optimal solutions. They just keep using their preset rules to set the incentives. But we consider the optimal solutions. And we can find, using our method, can find a congestion cost of very close to the exact system solutions compared with original UE. And there are some limitations for the TOP method and the GOE method. Thanks.